Welcome, everybody, to our July edition of the Akka.net Community Stand-Up. I'm here with Gregorius, and we have our guests from Echo who are going to be doing their Akka.net Show and Tell presentation in a few minutes. But first, we wanted to go ahead and dive in and talk a little bit about some of the work that's been going on with Akka.net since our last meeting in June. So I'll share my screen here. So we haven't done a major release of Akka.net yet. Since I think we did our last release at the beginning of June, although we're planning on a 1.4.40 release soon. That's going to include some configuration fixes for Akka.Remote and a couple of other little things here and there. So you should expect that in the next week or two. The big release that we that we actually did push is we made some pretty significant improvements to Akka.Hosting. And if I go to our releases here, the biggest things that we really did is that we went ahead and let me find this. Added some methods for supporting the cluster singleton inside Akka.Hosting. The biggest ones that we did, though, is we added some methods for being able to support Akka.Persistence much more closely. So we have a Akka.Persistence.hosting package now, and this makes it easy to add things like event adapters. So I guilty admission here. I added this because I needed this for a customer's project that we were working on here at Petabridge. We're doing a big CQRS sort of event sourcing application. And one of the things I actually need in order to do that is tags. I need the ability to add tags to some of my persistent events so I can create secondary indices for those. And the old Hocon way of configuring those is honestly kind of gnarly. It's not very easy to validate that you've done it correctly. It's kind of like how configuring serializers used to be before we added the serializer setup. Now we have a convenient method built into Akka.Hosting that supports that. We backported that functionality also to the Akka.Persistence.SQL server and Akka.Persistence.Postgres packages as well. So that's one thing that we actually did ship this month. Um, in terms of some of our future plans that we're working on, so I'll go ahead and add my little banner here for upcoming Akka.net releases. So some of the new things that we're working on, I didn't actually add my future plan here for Akka.Persistence.Azure, but we're going to go ahead and add Akka hosting support to our Azure table storage plugin as well. I need that for some projects we're working on here internally at Petabridge, so that'll be coming soon. That should make it very straightforward to go ahead and integrate Akka hosting with your Azure configuration. So no more Hocon needed to set that up. So that should be coming soon. Then in terms of Akka.net 1.5, wanted to go ahead and give some updates there. We have completely finished rewriting the test kit, so it is now fully asynchronous, meaning that there's no more methods that will block using a task.result or a task.wait behind the scenes. This should make it a lot faster for some of our tests to execute behind the scenes, particularly if you're running on .NET 6. That way there's no thread injection or any other issues like that. So that's been completed and is merged in. We also have, if I go back to the Akka.net organization here, we also have a number of pieces of work that we have merged in around, let's see, um, adding value task support to Pipe2 is something that we've added. We're working on bringing in iasync enumerable support to Akka streams right now, so you can consume an iasync enumerable as a source. We've had the ability for a while to go ahead and expose iasync enumerable as an output in Akka streams. Now we're kind of flipping this the other way around and making it so stream can be built around that. We will probably backport that to Akka.net 1.4 since I don't think it depends on any Akka.net 1.5 specific features. So that's something that we'll probably also make available as part of Akka.net 1.4.4 as well, 1.440 as well. So that'll be coming out. And other projects that have been ongoing inside Akka.net. Gregorius, do you want to talk a little bit about what we're working on with Akka.Discovery.Azure?
Yeah, sure. So we're currently building a new plugin for Akka management called Akka Discovery in Azure. It lets you um, basically create clusters inside Azure services such as app service and stuff like that. The only difference is that for other discovery, we usually use their built-in APIs and SDKs, but for Azure, we figured that trying to learn ARM, the Azure Resource Management system from Microsoft, is a bit too obtuse. and too hard to do. So we opted to actually store everything inside an Azure table. So all of the cluster memberships are going to be stored inside the table instead of us trying to pull it through their resource management system. The current development is going strong. I've only needed to make a couple of unit tests, make sure that everything works fine, and see it in action in the wild.
So,
Hopefully, in a couple of months,
well,
month
so
maybe.
in terms of getting a beta out there, we'll probably have something up on NuGet. Akka Management is sort of the parent project for this discovery component. And we've already had plugins available as part of Akka Management for a while. So, like the other ones that Gregorius was referring to, if I pull this up here, we have a Kubernetes plugin that uses like pod labels to go ahead and automatically discover nodes that should be inside the cluster. We also have an AWS version of this that uses things like EC2 instance tags. I believe we also have a version that uses ECS on there as well. With Azure, being able to go ahead and do things like inside Azure App Service doesn't really support the ability for us to like query what are all the different IP addresses inside an app service deployment. That's not something that's trivial to do, even with the Akka Management API, properly authorized. So what Gregorius and I sort of decided to do that would be easier is we're going to have each of the different Akka.NET nodes that starts up inside a lightweight PaaS platform like app services are going to essentially write some records that get expired from Azure table storage. And we're going to use that as our discovery medium. Um, and this is generic, meaning it could work in on-premise environments. It could even work in, let's say, other Azure services that we don't currently support. So it's going to be fairly generic in terms of the way it's designed. And this is ultimately to help reduce the cost of running Akka.NET on the cloud is what this is about. We want it to be able to run in lighter weight environments that don't require dedicated virtual machines or Azure Kubernetes service. So that's what this is really kind of intended to help us do. Um, I think getting the actual Azure Discovery plugin, a beta of that out, should happen relatively quickly. And then the next thing you're working on after this, Gregorius, is actually an end-to-end demo of everything running properly inside a cluster in Azure App Service, which includes having to document how to add things like a custom VNet endpoint and all that stuff. Is that right?
Yep.
Yeah.
Hmm.
So there's a little bit of work involved in that. In terms of some of the other projects that we're working on for Akka.NET 1.5, my big one for this month, I meant to have this all specced out before this meeting, but I've been stuck in meeting hell so far this week, so I haven't had a chance to get it up there. But we're working on trying to get a prototype of Artery, the brand new high-speed Akka.Remote transport that uses Akka streams internally. So that's something that it's going to be a big project. We're going to try to have everything in Akka.NET 1.5 delivered by the end of September. That's our hope. And I think we should have a prototype of Akka.Remote's Artery transport out by hopefully the end of August. And then a month of rigorous testing prior to making it available for production use. So that's what we've got so far out of our sort of labor since our last meeting. I would like to now go ahead and introduce our two show and tell presenters. So let me go ahead and add George and Jacob from Echo. How's it going,
Okay.
fellas?
Good. Thank you for inviting us in.
Yeah,
Going
absolutely.
great.
Yeah, absolutely. So, George, are you ready to go ahead and share your screen?
Yes, one moment.
No problem.
Still getting used to the system.
No worries.
So let me take this out. There we go. And then we
All
go
right.
into read mode.
All
There
right,
we
perfect. Well, I'll put you guys full screen and you have the floor.
Thank you.
go. Jacob, you want to start?
Yeah, I'll start. So just before George takes over on the technical part, I'll just give you guys a little bit of context to who we are and what we're doing. So George, if you could move to the next slide.
Mhm.
So basically, we Echo Sneaks and Data, or Sneaks and Data in short, as we like to call ourselves, was founded in 2017 by our founder René Madsen as a data science startup. basically with the initial aim of driving the use of data science and advanced analytics decision making within the family of eco companies. So you might have heard of Echo, the Echo brand as a shoe brand, but it's worth mentioning that the Echo umbrella also owns a list of other companies, small and large, including our little data science startup, which is now 15 employees. So as mentioned, we have around 5 years history at this point. We started with building, basically the first year we started building hardcore data science forecasting. Basically, our first product was built with the purpose of forecasting. Are we able to forecast the likelihood of selling, let's say, 1, 2, 3 pairs of shoes across an entire retail network, so other products than shoes for that instance. And then based on those forecasts, be able to take optimized stock decisions, such as like where to put the stock, how much stock to refill into the separate stores, but also when you're buying a pair of shoes online, where do we send it from to minimize waste on like distribution and so forth. And we managed to sell this product into one of Echo's larger retail networks in Europe in 2019. So basically controlling all these stock decisions across this retail network, across more than 20 countries. So that's kind of where we started. We expanded on that notion since and have now quite a few different algorithms based on these kind of principles. Back then, we were basically just data science, full stack data scientists who had the responsibility of pretty much everything from integrations to the actual data science to data transformations and to pushing these decisions onto the business. We've then expanded with data engineering and platform engineering efforts, and that's where George and I come in, and basically also where Akka.NET has come into all of this. And are building what we called an advanced data platform as a service. We've started that around 2020 and have come fairly far with that ever since. When we say advanced data platform as a service, it's because other than the data platform itself with the query engine and transformations and storage, we also handle stuff like cluster management, a little bit like you guys were talking about cluster discovery, data streaming, and also AI algorithm control. So those are some of the projects that George will talk about. But just to give you a bit of insight also to where we want to be going. So at this point, we are 15 employees and still growing fairly steadily. 6 data scientists, 2 platform engineers, and 2 data engineers, and then a couple of business functions. The idea is basically that we open source all of our solutions and offer them as open core across the whole market, so no longer only Echo shoes. Yeah, that's pretty much it. Then I'll move over to George, who's crafted a couple of really nice Akka-based algorithms or services.
Thanks, Jacob. That was a really nice intro. I would also put some words on how actually we got hooked up with Akka, or in my case, how it was a bit my personal story, but that really sold Akka to me, I would say forever. It's really short. So basically, the company I worked before, Sneaks and Data, it was an ad tech company, and we had this huge distributed hash tables stored in the thing called Voldemort, which is a huge, which is like an engine developed by LinkedIn where you can store terabyte-size hash tables that are accessible real time. And the task we had was very simple. We needed to copy a lot of data from our S3 buckets into those clusters when we got an update on the data we were serving. And then we had several data sets we needed to copy, ranging from, say, 200 gigabytes to like 5 terabytes. And obviously, the faster we copy, the faster we go live with new data. So the more money we will earn on auctions, because what we were trading identity information more or less in the auctions, and the more you know about the cookie, the bigger the value it will be for DSP, for example. So the challenge was that copying that amount of data from AS3, though sounds trivial, it's actually not a trivial task to do within, let's say, 10 minutes. So originally we had a multi-threading Java application that was doing that and was performing all right, but we had issues with high CPU load on the cluster while the data was being copied. And then we also had the problem that sometimes Amazon will, since you open a stream to S3 to get the file, sometimes it will miss like 1-2 bytes in that stream. So our checksum check will fail. And then we have to re-download the whole thing. And one other issue we had that sometimes we won't have this problem. So we seemingly so the cloud thinks it gave us all the bytes, but we haven't written all the bytes. So the final store that is on the live cluster will have like 7 bytes size difference from the S3. And the whole problem with Voldemort is basically if you corrupt one of the files that holds the keys, the whole cluster cannot initialize. And then you are not live. You can't serve new data, so all your advertising options basically stop working. And we struggled with that quite a lot because the problem was not reproducing with any pattern, so we couldn't find the actual root cause of it. We kind of nail it down to something like threads competing for resources, but we couldn't really understand what was going on. So at some point, we just decided to rewrite it and use Akka instead. And the biggest relief doing that, and that was in Scala back in the day, for me, the biggest relief with that was that we solved the problem with like 200 lines of code. And that was it. And we had automatic retries if the file checksum didn't match the one reported by the cloud. We had automatic retries of the whole thing if something went completely wrong. We had reduced CPU load while maintaining much better download performance. So actually our download speeds dropped from, say, for 1 terabyte, we had 1 hour time to download, and then they dropped to like 10 minutes for the whole store plus verification. And obviously we were not downloading to one machine, so it's to usually 5-10 machines at the same time. So that was my personal success, and our whole team that was working on that, because we also fixed the revenue problem for the company, and we solved it just using a smart code framework. That's just a little story of how I fell in love with Akka. And when I joined Snicks and Data, me and Jacob, we also worked on heavily integrating Akka in our processes here. What we do as platform engineering department here, we basically support large-scale analytics, right? So when you have a lot of data, you have AI or machine learning, or we also have a lot of optimization algorithms that is basically solving a very complex equation, to put it in a simple way. And we need to compute that fast. We need to compute that within reasonable time. We need to compute that within the budget. And then we also need to ship data for that, obviously. And the common challenges are listed here. So basically, if you want to stream data, you have low diversity in the streaming products available on the market. If you want reliability and error lineage and fault tolerance, that's not actually out of box available from any open source or commercial product. Then computational resources are not infinite, but data scientists tend to build stuff against infinite resource model. So we have to manage that somehow. And also many commonly used things like Spark, for example, they are not native to Kubernetes. Even though Spark, for example, has a Kubernetes sort of extension, it's not really working well enough for us to use it 100% in production. Also, other thing is that we live these days in containerized world, but many big data processing tools, they were developed before this era. So we need to somehow make them friends. we developed actually for our platform 3 main components, all based on Akka.NET. We have a thing that manages workload for Spark clusters, which provides a job queue that sits outside Spark, fault-tolerant scheduling, also HTTP interface, and also acts as a Kubernetes API proxy for Spark. Then we have an application that runs machine learning or optimization algorithms with virtual queues. So instead of actually having, for example, an Azure queue for this application, we use Akka's Merge Hub, Akka Streams Merge Hub to serve as a virtual queue for this application, for reasons that I will talk a bit later about, and with all the things that you see on the slide as well, which we'll talk in a bit in detail in a couple of minutes. And then obviously we want to stream data, because one thing is when you batch load data, let's say every 6 hours, every 3 hours, and it's completely different quality of your predictions and optimizations when you do it on live data, which for our use case is almost fundamental, because for example, auto replenishment works based on the information that you have about current inventory levels. And if you don't have up-to-date inventory levels, then your optimizations are, the value of the optimization you do is decreasing very fast. So we need some kind of data streaming solution. And obviously, the answer comes like, why don't you use Kafka? Well, I'm going to talk a bit about that soon. First, like, why did we go with Akka Streams? There are several reasons for that. One is Akka Streams really have the very simple programming model that a bit resembles, for me, with a guy with the Scala background, it resembles functional programming. So it's kind of double bonus for me, but also it resembles LinkQ a little bit. For people familiar with LinkQ, it's very easy to onboard people on Akka Streams. So it's very easy to, let's say, hire a developer who never worked with Akka and just give him a short crash course, and then he's already delivering code that is fit for production. So basically simplicity. Then you get a lot of things out of the box with Akka Streams, namely fault tolerance, retries. And then when we talk about managing execution of jobs in Apache Spark, then we have these 3 big challenges, right? We have Spark clusters, which have, let's say, they can auto-scale, but they can auto-scale to the amount of money we have. But the number of jobs and the volume of workloads that we want to run on these clusters is always bigger, because business always wants more than we can technically serve budget-wise. Then Spark doesn't really support auto-scaling in the sense as Kubernetes, for example, understands it. When you have node pools, right? And then there are 50 machines now, and then there are 10 machines 1 hour later, depending on how intensive your workload is. Spark doesn't work that way. Internally, Spark can auto-scale the executors that it allocates to certain jobs, but it can't scale the actual cluster that it's running on. The same goes for Yarn. So, for example, if you take Amazon EMR, they developed their own solution to auto-scale EMR clusters. And for almost 1.5 years, I worked with EMR clusters that were not able to auto-scale. So you basically we had to provision, say, 500 node cluster and just live with it, even if it was busy like 50% of the time. And that's a lot of money thrown away. And here because we also aim to serve a lot of customers, we obviously do not want that, because it's not financially viable for us. And then the queue management, obviously, in Spark is quite primitive. So you either have FIFO, you have fair scheduling, and then if you're constrained in number of cores you have, then you submit 1,000 jobs, and they just wait for resources, doing nothing. And then you have, let's say, 50 jobs just executing. And that is very suboptimal behavior. So what we thought when we developed this application, like, let's treat incoming jobs as events instead. And basically the message in the event is the job configuration. And then we will build an application that processes these jobs as an event stream. So instead of just saying, I received a job, now I need to run it, like what you do with Hangfire, for example, like one common library for background job processing, we will instead just build an Akka stream that processes these jobs. And then we will handle auto-scaling with Kubernetes horizontal pod auto-scaling. And that simple idea boils down to this very simple diagram. So how do we process this stream? So we receive a job request, our controller, for example, /job/submit, receives a request to compute something. We put it into a queue, and it can be whatever. It can be SQS, it can be Azure queue. It doesn't really matter for us. Then we put a Akka queue source on top of it. And we actually use Alpaca port for that, which is, I think, when we started using it, was still beta. I don't know if there was a release version.
It's still in beta at the moment.
But it works quite well. So we started using it when it was like beta 1, and now it's beta 8 that we have running in production, and we haven't had any problems with it. So I was always wondering, why is it beta? It's working so good.
I think it's that Gregorius and I wanted to write some more documentation for it, but we could probably take it out of beta.
Yeah, but it was pretty easy to just plug it in. So that guy is pulling messages from the queue and then sending it to the scheduling flow, which we'll have a look at the next slide. And then if the scheduling flow results in a success, so we were able to allocate the job, then we remove it from the queue. And if we can't, we keep it in the queue using just the simple visibility mechanism that every cloud or whatever queue you implement usually has. So when you pull the message out, you hide it, you don't remove it. And then after a certain amount of time, it becomes visible again for the pollers. And as you can see in the diagram, the whole thing is basically the Akka runnable graph. And that graph is plugged into a restart source. And the reason we want it in a restart source is because if anything goes wrong with the scheduling, we want, obviously, the polling to continue, and we want to keep going. And imagine if you had to write this using, I don't know, async enumerables or tasks in just plain raw .NET. That would be quite a task with all the retries and awaits and all the things that you need to put in. And most importantly, your code will, to a certain extent, will be blocking. While what I really like in Akka streams, that the whole thing runs on its own thread and is completely outside our control. And I'm happy about that. So I don't want to control how my stream is actually running. I want to control the logic inside the stream, because that is what's important for me as a developer. And how the whole thing runs is handled by the framework. That's exactly what I want from the framework. And then why Akka streams? Because you can build your application in this kind of thing where you put very top level abstract concepts. So I have a queue, I need a queue poller, then I need some scheduling. And then you say, okay, how do I write my scheduling? Let's get into that. And Akka has this awesome concept called flow, where you can define some input and some output, and then the output can be passed downstream to whatever is happening after that. And we define our scheduling as a flow, more or less, that receives a certain information about the job, so buffered request in this case. And then we have a certain number of clusters that we can run this job against. And then you can see that we can select a cluster as a part of the scheduling flow using another flow called select cluster. Because obviously when we receive a job, we need to put it somewhere. So we need to decide where it goes. And the way we build this application is that we can supply a list of rules that are injected as a part of application configuration that are also small flows. So each iCluster selection rule is actually a flow that you run as a part of cluster selection flow. And then each rule produces a score. So for example, this cluster doesn't fit this request, then we return -infinity for whatever reason. For example, the request might say, I want to run on on-demand machines. So all the spot clusters do not fit this request. So we just return -infinity for those clusters. Then another cluster might not have enough capacity right now to run this request. So we will return some score that is close to 0 or negative, depending on the capacity that it has available. And then the other cluster might be quite good. So we'll return some positive score, depending on how the rule evaluates the actual score. And then in the end, we will aggregate scores emitted by different rules for each cluster, and then we will select the winner and pass it down to the activation flow. Because one other thing that we do is we do not keep clusters running all the time. We want them to respond to the workload in a proactive manner. So if we receive a request and we see there are, say, 5 running clusters and one is sleeping, then okay, that's good for us. Maybe we do not need to wake up the sleeping guy. We still have capacity on the new ones, but sometimes we need to activate a cluster. And that again is a separate Akka flow. So it's here. That will, I will not go in details how activate actually works. I just put this small snippet here. So basically we have Spark has 2 stateful sets, the one for master and one for worker. And then when activate is called, we just check that they are scaled. If they are not, we run a scale, another flow, another Akka Streams flow that scales these stateful sets. And then this will, we can concatenate the results of those scale outs. And when they are both done, we return the node address that is ready to use. And then obviously we can fail to scale for multiple reasons. For example, Azure refuses to give the machine. That can happen. Or the giving us the machine takes more than time than we expect. And this is the brilliant thing in Akka Streams, that I can allow my code just to fail. I can basically just throw an exception, and that's what we do. And then if we go back here, we have this restart source guy, which will catch this exception and retry everything when the message becomes when the request becomes available in the queue again. And let's say we have this just as a application configuration when that will happen. I think it's like 15 minutes. So basically we are acting on assumption that you have 15 minutes to schedule one job. And if you can't do it, then we'll schedule it again. And if we can't do it, we just fail. And that makes writing code super easy in Akka Streams, because I don't need to think twice what to do. Like, do I need to return like empty value here and then decide what to do with it? Do I need to return null and handle it in a special way? I just throw. And then I actually can put nice information in my exception. I can put a metric on it, and then I can see all that in my whatever Elasticsearch, or we use the Datadog, or whatever solution you use to monitor your applications. And then if we succeed in activating the cluster, then we have another small flow that with the same idea of rules, which allows us to configure the request. This is a bit specific to Spark, so we can tell how much memory should be used for this job, how much CPU cores should be allocated to it maximum, or how much space it is allowed to take on the cluster in general, and some other job-specific configurations that affect cluster performance. So we set them here. And then in the end, we produce a configured request and a cluster that is ready to run it. And then we ship it to the cluster. And the last thing that we do is, you will see it a lot on my pictures here. We checkpoint, we use Azure Tables as a metadata store where we put basically some information that we need to report the status of what's going on, and also to track what's going on. So this is where Akka Streams really shines, because we receive, let's say, I think several thousand compute requests per day of different kinds, different Spark jobs. And we have this simple system that is handling them one by one, because it's all basically one thread. So we have one request, we pipe it into scheduling flow. While this guy is being reviewed for the cluster selection, another guy is being pulled out, and it's just like a conveyor of jobs that is going in. If something fails, we restart. And also the beauty of this, that we can deploy this application at any moment in time. If it's busy scheduling, it will just restart when they become visible again. So it's completely stateless. We do not care if we break the current scheduling process, because it will start again without any intervention from our side. Then other nice thing that you can do with Akka Streams is to have process supervision, which we rely a lot on, because when you have these sort of asynchronous, or I know it's not right to call it asynchronous, but a separate process, let's say, that is doing some logic, and you want to monitor that process. So for example, in our case, we want to see, has the job finished on the Spark cluster? Has it failed? Where are the logs? So what do we tell the guy who launched it? And that you can easily do just defining Akka graphs that do this supervision. So for example, we have supervision flow that reads the checkpointed, so the saved job requests from the NoSQL store. So in our case, it's Azure Table. Then retrieves the cluster information from this JSON that it receives, checks, is it done? If it's done, then it will archive the logs, mark it as completed. If it's failed, it will mark it as failed, archive the logs so they can be read. If it's running, it will just repeat. And I do not need to write any loops here. I just write the Akka graph, and then I run it in my hosted service. And that's it. That's pretty simple. And yeah, it's just plug and play, basically. Then other thing that we had to solve was how do we run a lot of predictions and optimizations at the same time? Because when data scientists is developing the algorithm, they usually run it locally a couple of times, and it's not hard, obviously, to do. But what about if you have like 1,000 predictions per second coming in? You need to accept, schedule, execute them, and communicate the results back to whoever sent that. And then you need to do that 24/7. As an example, we had a case when we had to compute redistribution of products between stores, warehouses for 10,000 SKUs, which is like 10,000 parallel computation for one request. And the way we do it, we ended up doing it, is using Merge Hub. Because Merge Hub is a many-to-one aggregator, right? So you receive many events, and then they are piped to a single sink, to a single destination. So in our case, we launch Kubernetes jobs for our optimizations, because all of them are containerized. So the natural way is just to launch a Kubernetes container in Kubernetes and get the job done. And then we just need some way to schedule it with minimum time. because scheduling time is important. We have some algorithms that are kind of close to real time, so we need scheduling to be the minimum there. And then you need to run it, obviously, and get the results back. And Merge Hub is ideal thing for this because normally when you have, say, a high load API, you need to come up with some sort of batching procedure for that API. Or put a queue in front, right? So you put your incoming requests in when the load goes over a certain amount, and then you will pull that queue and gradually process them. With Merge Hub, and obviously that introduces latency, right? Because you need to write things in the queue, you need to get them out of the queue. Getting out of the queue is polling procedure, and then you're in all clouds, you actually charge for that. So it's not really ideal for, as we thought. So we thought, like, why not just use Merge Hub, where we can have a simple controller action which adds the payload to the Merge Hub, and then Merge Hub will pipe it into Kubernetes. So our sink will be a Kubernetes, where we basically the process where we create a Kubernetes job. And then we put a horizontal pod autoscaler on top that will just spawn more pods with more Merge Hubs when we have high request rate, and then we'll shut them down when it's normalizing. And one thing that Akka gives you here is you have throttling out of box. So also, because obviously Kubernetes control plane and Kubernetes API, they are running somewhere, so you can't just send thousands of jobs there per second. You need to normalize your request rate to Kubernetes, and Akka helps you with that by just plug and play again. And you can normalize your incoming request rate as well, so your application, the processing pipeline is not overloaded, which is just excellent. It's just two calls, and then you have a steady data processing pipeline. Of course, Merge Hub can kill your application because you can just run out of memory if the request rate is very high. And that's why we build a speculative scheduling substream, another stream that does speculative scheduling. So basically, we supervise the metadata table again. And if we see that some of the requests that we received are sitting too long in the queue, we just pipe them in another Merge Hub, which then sends them directly to Kubernetes again. So that is sort of the same thing that Spark does with task execution. When it, instead of launching one task, it can launch up several copies of the task, and whoever wins the race then is the one who completes the job. And that solves the problem with restarts for us as well, because as long as we can receive the workload and serialize it, we can always pick it up by another Kubernetes pod can pick it up and send it to launch a job. And the same goes with result processing, because when you have 10,000 parallel computations completing at the same time and sending the results, you need to you have some work to do, and you don't want to exhaust your thread pool with that. So we also communicate results back using Merge Hub. Because basically what happens, the data science container or the machine learning container will finish the job, and then it will send us the result of that job or whatever it was doing. And then the request that it sends, we will put that in the Merge Hub. So if there are 10,000 containers here, they will all go through Merge Hub one by one, and we will perform the bookkeeping operation that we need so the client can actually read the results. And then, the last topic is data streaming. So how do we manage streaming workloads? Basically, as I said, Kafka and Kinesis or no streaming. That's kind of the state of things these days. But the problem is that this is no variety at all. And then you require specific setup and knowledge to actually operate both Kafka and Kinesis. And hiring for these products is problematic. And then if you want to on Azure, like Kafka implementation on Azure in what's called event grid, it's not really ideal. Let's put it that way. So if you want more functionality, you have to either go raw Kafka and maintain it yourself, or go AVS. So we thought maybe we can just build something simpler, something that is not as powerful as Kafka maybe, but that is very simple for everybody, not just us, to configure and use streams. And we thought like Akka Streams is the ideal candidate for that. One thing we where we wanted to have in this application is to use Akka Remote to dynamically provision actors from Kubernetes cluster. And I think, Aaron, you mentioned that that would be a coming feature.
The ability to go ahead and provision actors from Akka.Remote?
Yeah, from Kubernetes cluster. So use provision actors from Kubernetes cluster using Akka Remote instead of using threads.
Gotcha. Okay. Trying to think what feature you're referring to, actually. Let's say we do have our Kubernetes-based service discovery and all that. But you'll have to follow up with me offline to refresh my memory on that one. No worries. But anyway, so you said you looked at using Akka.Remote for some of your streaming systems?
We wanted to use Akka Streams, but I wanted Akka's actor system not to use the local machine thread pool, but to use actually the whole Kubernetes cluster to give actors to my Akka Stream.
Okay, yeah, you actually can do that using stream references in Akka Streams today. That would allow you to have basically like a source that basically exists on one node and a sink on another node that can run your graph that way. So that feature made it into Akka.NET 1.4, and we do have documentation on it, but what we don't have are any tutorials on how to actually really like design with it, if you know what I mean. So
yeah, that's probably what we were missing, because I kind of tried to set it up and then I thought we will go with an easier approach, which I'll just describe now. So what we thought, we will just launch a certain number of streams per application instance, and then when we need more streams, we'll just launch more pods that run a certain number of streams. And then the thing that we wanted from Akka Streams here is the ability to externally control a stream, because what you want with your data streaming is you want to turn it on, and sometimes you want to turn it off. You want to restart it with different configuration. You want to know how much data is going through your system, who is sending that data, where is that data going. And Akka actually gives a lot to do that. And one of the biggest things that you have with Akka is a kill switch. So you can just add a thing called kill switch to your stream, which allows remote termination of the switch of your stream, which is shown in my code snippet here. And it's as simple as that. And then the return type of your stream is basically, so since we do keep write, it will be a kill switch. And we basically just store it in our application memory. And if we need to kill the stream, we send an API request that finds that kill switch and turns it off. Then other thing that we were looking here is obviously error recovery, because when something is running, let's say for months without interruption, and then one day it goes off, you want to know why. And you want that to happen automatically without you having to browse anything, so that you can see it in your monitoring system. And again, Akka Streams has this wonderful thing called recover with retries, which is just part of your stream, which allows you not just to catch an error like we're doing here, but also we add a separate call to actually process that error, write the error information in the metadata store we use for this application, so we can have a full stack trace there as well. We can also see that the stream has failed and why, and then act on that, because then the system that, for example, is handling stream states can decide, do I want to restart the stream or do I want to signal a red light here? Then the ability to obviously write whatever you want inside stream transformations allows us to send metrics as a part of the stream code. So basically here we have a source that sends some rows that we group, that we convert into lists to create a parquet schema out of that list. And then we also just send a simple metric, which says this is the number of rows that I received. And we see it on our dashboard, and we can see which systems are sending rows, which systems stop sending rows for some reason. And then the last thing, obviously, the ability to write your own sources in sinks, which this application that we developed allows us to do. So we can, if we want to stream from whatever place, we just write our own source. And then we have a set of sinks to commonly used, data formats commonly used in data processing like Parquet and Avro that we can just plug in here and get our Parquet files out of the box. Just for comparison, in Kinesis Firehose, you can also sync to Parquet, but there is some setup that you need to do. You need to get the schema going from somewhere. So here we actually make that as a part of the source code. So your source is able to produce a schema for your Parquet sync or Avro sync if you're going for that for Avro. And then you get your problems solved automatically just in one small code piece. And that's it for my talk. I hope it was not very long. And I think we are open for questions if there is or
no, your talk was the perfect length. And yeah, right on time for about 10 minutes of questions. I appreciate that. So I think that this is the first time, we've actually had anyone give a presentation on, let's say, like genuinely a big data problem with that Akka.NET plays a role in. And in your case, it's not necessarily that the volume of data is unmanageable. It's the volume of work that has to be done on a finite amount of resources that's the issue. It's like a workload problem. And so I think your solution for using Akka streams to go ahead and dynamically kind of allocate which Spark clusters are going to receive which job based on which ones are available is a very interesting solution to Spark's own like simplistic scheduling algorithms. I really thought that was a clever design. The other thing I wanted to know about was your Merge Hub applications. So is there ever any issue with running multiple of those in parallel? Like, basically, does each one they're all launching their own Kubernetes jobs, I guess. Is there any reason why there'd be a problem running multiple of them in parallel in terms of having multiple merge hubs, all their own separate jobs, not really interacting with each other? Or does it not really matter depending on this type of workload?
So in this case, each application runs one merge hub.
Okay.
So each pod is a single queue, so to say. Of course, that's not entirely true. So we have a receiving merge hub, the speculative one, and then the one that sends. So actually, one application runs 3 merge hubs, right? So they all have one. Each of them has a single purpose.
Gotcha.
We haven't seen problems with that. So we tested that with I think the biggest test we ran was like 10,000 compute requests per second. The only problems we have seen were actually Azure Kubernetes service not being able to process that amount of workload.
How big is your Kubernetes cluster typically? Like, what's the total number of VMs that are in it?
So for this application, we have, if we're telling in nodes, I think that's like there are 3 node pools, each of 35 nodes in it, or something like that. And they have machines varying from 32 to 128 gigabytes of memory right now. That's for this application. And then we also have another node pool there for which hosts 20 nodes. So the total is like 100 plus 110-ish nodes, and the memory capacity of this cluster is like slightly above 1 terabyte. So it's not a huge cluster. It's okay,
Gotcha.
I would say. For Spark clusters, we run like the whole thing here runs on top of a not technology, but something we call Spark Swarms. So it's actually a Helm chart, a Spark Helm chart installed inside a Kubernetes cluster. And instead of installing one Helm chart, we install, let's say, 6 of them. So each Spark Helm chart is one Spark cluster. And we have each Spark cluster is 35 nodes. We run currently, so we have 3 main ones which run production workloads, and then we plan adding 3 more for this specific setup. It's actually this week I need to do that. So in terms of memory, CPU, it's like around 1 terabyte that we use in terms of clusters memory size.
Very cool.
And we use smaller machines because they launch faster. One of the things that, for example, that is a big problem in AKS, the big machines, they launch very slowly. And the image pool time is very low, is very high. So you want to use smaller machines. So at least the machine startup time is very low. So let's say like within 3 minutes, and then you add the image pool, let's say another 30 seconds on top.
Got it.
And everything is so it's auto scaling. So they are not always at that size. So for example, the cluster can be just 10% of maximum capacity first 3 hours of the day, and then it's full capacity depending on what's going on.
Gregorius, did you have any questions?
No. It's very interesting, but it's pretty clear.
Well, I had one more sort of 2 questions for you. So first was, you talked about your exposure to the original Scala Akka at a previous job. Why did you end up going with Akka.NET on this one? I think you might have covered it very early on, but I don't remember.
Actually, I don't think I did. So
Okay.
let's say, one thing, our main stack here is C#. So, and introducing Scala to your team is not an easy task, right? So Scala has much higher entry barrier than C# in general. Then there are way less developers that have Scala skills that you can hire on the market. And the other thing is that C# in general has a lot more features when it comes to comfortable application development compared to, in my opinion. I'm not pushing it on anybody, but my opinion, there are a lot more tools for comfortable application development in C# and in ASP.NET, right? Compared to Play framework in Scala that I used to work with as well. There are some nice things, but yeah. And then the other thing was that basically you don't really like, there is a lot of stuff in Akka Scala framework, but many of them are there because somebody needed them, but they're not really widely used. And what actually I liked in Akka.NET, that you have the core functionality, the ideas here, and then there is not much fluff around that is on documentation, but you don't really know why it's there, sort to say.
Got it. Yeah, well, basically it's kind of funny. I guess it's the fact that we're not a big, $70 million venture funded company like Lightbend, where we have the ability to go and build stuff out for individual customers and create feature bloat. I guess actually that comparative weakness is actually a strength in some respects, right?
I would say yes. So, when I first looked at the repo, I was like, how could they build something so huge, ported, and it will be working? And then we laid out this first application, this workload manager, just in the very broad code. And then it just worked. We were like, okay, this looks solid. So let's try to build something on that. So I was actually very positively surprised when I saw that such a huge framework, as I perceived it can be reliably ported and actually work really well. including stuff like Alpaca extensions, right, which is completely stuff on top
Yeah,
of the framework.
absolutely. Well, we've got a big, Petabridge, obviously we commercially support Akka.net, and we've been doing that for a long time, but we also have a huge community of users that actively contribute and use it too. Alpaca is a good example of a library that's almost entirely user driven. I think the only part of it that was like truly designed from scratch from the very beginning, like as a result of a commercial need that Petabridge had, was the Kafka integration. I think that's like its own separate repo because it's pretty big. That's the only really, let's say, big one. The rest of them where we had customers that wanted to use Akka streams for talking to Rabbit or talking to Azure Event Hubs or talking to Service Bus, and they wrote a version of it themselves. And Gregorius and I and other members of the contribution team have maintained them and cleaned them up over the years. But they were all sort of original creations of actual end users for the most part. Which brings me to my final question for you guys before we end our meetup for today, which is, what are some features or things in Akka.net that you and your team would like to see in the not too distant future? What are some things we could do to support you?
Jacob, do you want to start, or should I?
Go ahead.
I would say when we go to the streaming application, right? Back to what I mentioned, more or less. So because we work 100% inside Kubernetes, it's very important for us that the framework, is not afraid of Kubernetes and feels kind of native inside it. And that's one of the reasons we actually build, right now, we build Akka Streams applications in the way that they do not know anything about Kubernetes, just to not to have any problems with that. But what I would really like is to have as I said, my actor system actually be aware of a Kubernetes cluster. And if there is such functionality, then I would like to understand how I can efficiently use that. Because if I can bring you an example here, so if my data streams, right, one thing I can run source on one node and sync on another node, that's cool. But what if I want to run actually my data transformations that are part of the stream on different node? So what is happening? Let's go here. So what is happening in between source and sync? For example, here. I don't know if that's possible, but I would imagine that would be nice.
I think it should be possible using stream references to model that. You would basically would just take a normal flow and you would model that as a substream basically inside of it, is how that would probably work. So,
Okay.
That's more of it. But what you're asking for is kind of more of like and I've never done this myself before either, so I can't even tell you how to do it off the top of my head. But it would be something more along the lines of using Akka.cluster to discover those new Kubernetes pods that come online and being able to use that information to figure out where are sources inside my cluster that I need to attach to in order to do my job. So being able to basically connect hubs and stream references together using data from the cluster to create some dynamic sort of scalable, horizontally scalable processing.
Exactly.
I think all the building blocks are there. It's more of a matter of we need to have a pattern that kind of makes it easy to reason about. And so, yeah, that's actually kind of a fun, that sounds like a fun challenge, actually. So that's something I'll go ahead and give some thoughts on that. We have a repository that we've been updating with some more like modern infrastructure examples of Akka.net. So I've got one on how to do reliable messaging with Alpaca using RabbitMQ and Akka.cluster. Got another one on Razor Pages, which is mostly about how to use Akka.Hosting to kind of integrate things like shard regions into your app. But maybe doing one around how to use stream references would be a good use of time as well. That's something.
Yeah, I would say actually that I would definitely like to know more about that.
That sounds like a good idea. Well, gentlemen, I want to thank the team at Echo Sneaks and Data for their really awesome presentation. This was really helpful. Appreciate it. Appreciate it tremendously. These little insights into how people use Akka.net in the real world really help our users a lot. So it's always a really big help to everybody when you do that. So we appreciate you and your time. So thank you.
It was a pleasure.
Thank you too.
Yep.
It was a pleasure.
Now, if anybody attending wants to participate in a show and tell in the near future, we'll include a link to that in the description. Otherwise, don't forget to like and subscribe. So go ahead and like this video and subscribe to our channel to get notified about any other new YouTube videos or live streams or community stand-ups we're going to do around Akka.net. So thank you very much, and we will see you all next time.
Thanks a lot.